record? Is it recording?
It should be.
Okay. So is that readable to you guys? I don't know. That's kind of like what. Obviously, that says presheaves, but if anything is unreadable, let me know. Because these were I was gonna rewrite these, but then I figured to save time. Okay, so first chapter is kind of not too crazy, pretty basic. Probably many of you have seen these things before, probably presheaves and stuff. I'm going to assume that you guys know category theory, but if we need to like review something or slow down, just let me know. But okay, so first thing, a presheaf. Let A be a category. There's some size. Say size. There's some things about size, like subtleties about size, which he talks about in one of the remarks at some point, but we won't really go into that much at this point. From what I've heard, it's not as big of a deal as it seems at first, but it is a subtlety, and you should keep in mind that there are size things. Like maybe if you want to be happy, just assume this says small category or something. But okay, let A be a category. A presheaf over A is a functor that looks like it's a contravariant functor from A off into sets. And so for each element A and A, we call its kind of fiber X of A, or that's the image of A under X. And then for any morphism U in A, we call the image under X this U star. This isn't in the book. This is just how I kind of visualize presheaves for some reason. But if that doesn't help you, then ignore it. But that's just this is my rough notes, so that's why I drew that. But so at each kind of object, I draw categories as kind of blobs because I think of categories as kind of almost like spaces, sort of. And so at each object in the thing, each object is like a point in the blob, and then each morphism is like a path in the blob. And so for presheaf, to me, it associates each object to some kind of, this is like my way of visualizing a set. Okay, anyway, this is a bad like metaphor, so maybe don't get too hung up on that. But there's an example of like open sets on a space. This is like what you see in algebraic topology, is this kind of presheaf, right? Okay, and then a morphism presheaf is a natural transformation of these type of functors. And we collect these into a category. I don't remember what he calls them in. Oh, he calls this a hat. Sometimes I might write the script PA or PSHA for presheaves, but I'll try to stick to this a hat notation that he uses. Some other people use these other things, which is why that's how I learned them first. Okay. And so we collect these into a category. We can form a functor called evaluation for any object A, evaluating at A, that is sending a presheaf to its fiber at that point. This functor preserves limits and colimits. That's the statement of this remark. There are some other things he talks about as well. But this is useful because, as he says in the book, limits and colimits of presheaves can be calculated locally, that is, or some people might say pointwise. And by pointwise, they mean like at this point, at some at the point at this object A and A, you can calculate kind of limits and colimits. This is nice because instead of calculating a limit of presheaves, you can calculate it in sets, and or the same with colimits. And limits and colimits of sets are obviously a lot easier than presheaves. So explicitly, that means kind of like we have a family of presheaves xi indexed by some, might have to be small or something, maybe not. We have some family of things and we want to calculate its limit or colimit, then x is the limit of this guy if and only if each fiber of this guy is the limit of the fibers of each xi's. Hopefully that made sense. Sorry, I'm still waking up also. Again, interrupt me if there are any questions or remarks. Your sets, okay, then this one is important. Yoneda embedding. There is a functor from A to presheaves over A that sends any object into the set of homs into that object. This is why I kind of thought that we might have to assume that A is small because these might not be sets, but Cisinski calls this H sub A. In Lurie, sometimes if you're reading Lurie, he uses like a little j for this guy, for this H. And some people use the Japanese yo for those. But I'm going to try to stick to Cisinski's. Probably most of you guys have seen that anyway. And so Yoneda lemma for any presheaf X over A, there's a bijection between fibers of X and homs from the representable thing at the A into X. So he writes down this explicitly, at least going in one direction, which is this here. So mapping a map of presheaves gets sent to this image of whatever the thing on the fiber on the identity of A. You can check the book for this more explicitly. And I also wanted to mention that there's, I think, a typo in 1.1.6 where it should, oh yes, he has F from A to X, and there should be F from H, A into X. Not a big deal, but there's a typo. Okay, and then another way of saying, sometimes the Yoneda lemma is stated like this, as he does in the book. Then sometimes people also include this part as part of the statement of the lemma, which is that the embedding is fully faithful. In Cisinski, that's written as a corollary, 1.1.5. Okay. And category of elements, or some people call it like Grothendieck deconstruction, is a category A / X whose objects are pairs. They're pairs where A is an object in A and S is a section. So it's a section in X sub A, the fiber. And morphisms in this guy are a morphism between A comma S and B comma T is a morphism in A. This guy is in A such that it sends this section to the section S, sends the section T to the section S. So this is my kind of cartoon of that. Right, and then some people write element of X or what we call this integral sign over X sometimes. Alternate notation, but I'll try to stick with Cisinski's. And then also, I guess, alternately using kind of Yoneda's lemma, you can think of homs as alternately being maps between presheaves, right? We can kind of pass between these two. You can think of these as maps between presheaves that make such a thing commute. Sorry, we can associate sections with maps between. You can associate a section S to a map H, A to X, and T. So alternately, you can think of morphisms in this category as being such guys. Okay. Now, there's a faithful functor that sends from category of elements to category of presheaves. That kind of works like this. You can check the book. I don't think this comes up anytime soon, but okay. Is that in focus? 1.1.8. Right. Okay. So this these maps S. Sorry. Given A and X is above, A is a category and X is a presheaf over A. Then you can write X as the colimit of these phi X's, these guys, over this category, where the maps going into X are the section. So phi X of a pair AS is this representable guy, and then or representable guy, and then maps into X are the sections, as we talked about in Yoneda lemma. And the statement of this proposition is that we can think of X as a colimit of these guys. This is my cartoon, which now I don't really know what it's saying, but you can decipher it later on. So these are the phi X's. These are going from A slash X to presheaves, sends a pair to this representable guy. Actually sends any A comma S or A comma S prime, right? All the things that are associated to A get sent to this HA, and then all the things associated to B get sent to this guy, and then I'm just writing this as a colimit of A over X by X. Right, and sometimes the kind of informal way of saying this is people will say a presheaf is a colimit of representables. Right. Okay. Some people also call this a density theorem, which I just learned, but I had never seen before that. And then I guess this is where he talked about the size issues, 1.1.9. I don't know if I wrote anything down. Yeah. So remark on size issues. You can read 1.1.9. I won't go into it because first of all, I don't really fully understand the size issues, but I know that they're not such a big deal in the end. But it's worth knowing that they're there and probably reading about it. Maybe someone can give a talk about size issues at some point because it's kind of interesting. But they're usually fixed with things like universes, Grothendieck things, or stuff like that, or assuming certain categories are small or locally small, whatever. Okay, and then we get to a big theorem of this section, which is, well, first let me talk about smallness and locally smallness, what he takes as his definitions in this book. So a category is locally small if for any two objects that the set of humps or the collection of humps forms a small set, which means different things depending on what universe you're working in or whatever, but for us, we'll say, for example, just a normal set. And then we say category small if it's locally small and it's all its objects also form the small set. Okay, and then we get to the big theorem, Kahn's theorem. I wanted to actually read the paper that this came from, but did not. I think I read it at some point, but it's like from 1958, some paper where he defines adjoint functors in the first place, and then probably writes on this thing. But so let A be a small category, C be a locally small category that has small colimits. Hopefully you know what that means, but if you don't, that means you have some diagram like I that is a small diagram, and a functor, then its colimit exists. And say you have a functor U from A to C. Then we define this. Then he defines this functor U star from C into presheaves over A. That sends an object into this presheaf U star Y that's defined in this way. So it takes an object A into the set of Homs in C from this U of A into Y. A little bit of a brain bender, but it'll make more sense when we see like a concrete example like simplicial sets. Then the theorem says that there is a left adjoint to this called U shriek or U exclamation mark. That is called the extension of U by colimits. And the reason it's called that is because this guy is the left adjoint, this guy preserves colimits. And we can define a sort of universal property of this, which is that like for any, I wrote it down later, but yeah, I'll write it down later. But okay, so moreover, there are unique natural isomorphisms for all objects A and A between U of A and this guy of its representable thing. So these are objects in C, and so this is an isomorphism in C. Sometimes I get confused about where these things are living. So this is my cartoon of that. This is A. This is the presheaf. This is Yoneda embedding. This is the functor U, C, and then this is U shriek. So going like this, we have a natural isomorphism in here, right? And then these natural isomorphisms are such that they play well in some sense with Yoneda's embedding and stuff. This is the isomorphism that comes from the adjoint, right, between Homs and C and Homs and presheaves. You can read the book for more about this. He goes into more detail about this. Okay. Any questions or comments? Okay. I guess the idea of what I was saying before is that because we can think of presheaves on A, as we learned that presheaves are complete and co-complete, that they have all small limits and co-limits. This is why we can think of this guy as an extension of this by co-limits. That is, we're kind of formally sticking in all limits and co-limits. Now there's some subtlety with that, which is like sometimes passing to a presheaf can get rid of certain limits or co-limits that might exist in here, and then you have to like do something like sheaf, like impose some relations and turn it into a proper sheaf to get those limits and co-limits back. You can read there's a paper called like presheaves. I think it's called Presheaves and Homotopy Theory. It's a Duggar by Daniel Duggar. It's kind of interesting paper. If you're interested in that, you can read. That's not super important. Okay. This is what I was trying to say. Extension by colimit. So that is any colimit preserving functor from presheaves into C can be written in this form. Let's say if you have A hat, C, you're starting with a functor like this, then they're saying that you can write this as U shriek for some U like that. Okay. 1.1.13. So let A be a small category. Then the category of presheaves over A is Cartesian closed. That is, it has a sense of a Cartesian product, and it has an internal Hom functor that is an adjoint. So products are not too hard to define. You can do this as an exercise if you want, or look it up. It's not really that difficult. Basically, products are defined as we learned. We can compute limits and co-limits pointwise. So products are basically boiled down to just products of sets of the fibers. And the internal Hom so the internal Hom takes a pair of things and forms a presheaf out of them. And these are adjoints in this way. That is by how adjoints work. That is, we have natural bijections of this form. Right, so Homs from a product into Y are the same as Homs from this guy into this Homs. You've probably seen things like those. These is Cartesian closed. Right, and then 1.1.14. as we talked about, I kind of wanted to skip over this one, but it's kind of like a growth and deconstruction, but not super relevant to us immediately, but we'll see this come up later. I'll let you just read that on your own. Okay, let's get into actual concrete things. Simplicial sets. Oh, there's someone. Oh, thanks, Logan. I will read this later. This is too much to read right now. But yeah, size issues. Maybe you can give a talk about size issues. That'd be cool. Okay, so simplicial sets. First, we define a category called the simplex category. We usually write it as a bold delta. Objects in this guy are finite posetsets. Oh, for me, should mention notation and includes 0 to me. So to me, 0 is a natural number. So if I write things indexed by n, I always include 0. So objects in this guy are finite posetsets. We'll write them as brackets n. And so this guy consists of a linearly, you can think of it as a linearly ordered set. We can also think of this as a category. We'll see that interpretation soon. You can think of this as a category where a less than or equals is a morphism. And then obviously in a poset, you can compose, right? So yeah, and then morphisms are just monotone, that is order preserving maps between posetsets. Okay, this we can ignore. In particular, there are special maps called coface and codegeneracy maps, written delta I and sigma I. This guy goes from n to the next highest one, n plus 1, and this guy goes from n to the lowest lower one, n minus 1. There are cartoons of what these guys do. So delta I, this is n, and this is n plus 1. So delta I maps everything up to I minus 1, and then I it sends to the next guy, I plus 1, and then everything else it shifts up 1. Sigma I didn't draw, but it kind of does the backwards thing where maybe I'll show. Drill picture in this is my thesis. So this is delta I and this is sigma I. Okay. Right, so those are special maps called coface and codegeneracy maps, and it turns out that it's not hard to believe, but it's kind of annoying to show, but you can see it in like the Gorse and Jardine book, Simplicial Homotopic Theory, where these guys actually generate all these types of maps. So any monotone map in this category can be written as the composition of these guys. So these generate all order preserving maps. That is, any map between n to m in the simplex category can be written as a composite of delta i's and sigma i's. Not too hard to believe, but annoying to actually write down. But yeah, so this is nice because when we're checking things about simplicial sets, for example, in some sense, you don't need to, like, you only need to check them on face and degeneracy maps and then say that any map can be written out this way, or whatever. Okay, so a category of simplicial sets. Simplicial sets. Sometimes I'll write as sets is this category of presheaves over the simplex category. So objects are functors from delta op to sets, and then morphisms are natural transformations between such things. That's kind of the category definition, but you can, in what that boils down to is a simplicial set X consists of a bunch of sets, xn, indexed by natural numbers, and again, natural numbers include 0 for me, and a bunch of maps, which all we really need to check is these images of the coface and codegeneracy maps. We'll call those DIs and SIs. And I guess I should mention this is for I. equals 0 to n, right? I can be anything. So there's a bunch of actually those maps. So he'll, I think in Cisinski, he'll write like D upper I n or something, just to remember that this guy, the domain of this guy is n, and so on. But that's kind of messy for me. I'll just write DISI with the understanding that this is known. Okay, and then for any n, there's a simplicial set called the standard n simplex, and that is formed by Yoneda embedding these finite post sets. So we'll call that for each n. There's a presheaf. This is in categories and simplicial sets. So this is H. This is Yoneda embedding H of the bracket n, and that's Homs in the simplex category from blank into to that guy. Okay, these guys are kind of the building blocks of simplicial sets. One way to think about that is like we learned that any presheaf can be written as a colimit of representables, and these are our representables. So any simplicial set can be written as a colimit of these standard n simplices. Okay, so given a simplicial set X, we call its fiber the set of n simplices of X. Okay, and you can think of that as Homs from the standard simplex into X. Okay, and yeah, by Yoneda, we can think of an n simplex given an n simplex alpha in Xn. We can associate that with the map from the standard simplex into X using this. One point, and then what am I doing here? Right, any morphism. Again, these are my notes, so I was trying to write all these down. But any morphism between standard simplices can be written as a split FE and a monomorphism. Yeah, you can check. This is 1.2.6. You can check Cisinski from 1.5. Okay, and then this is a good example. So for any, oh, sorry, if I forget to scroll, you should mention because it might happen often. But I don't remember where it's up. So this is standard n simplices, the set of n simplices of X. We can confuse those with maps like this, and then that small remark, and then the interesting example topological things. So for any n, there is a topological n simplex, which you've probably seen in algebraic topology. There are different definitions of this, which I didn't realize, but some people take, I don't know, they're slightly different, but in the end, they're the same thing. They're just whatever Euclidean space they're embedded in or whatever. But there's a standard n simplex. We write it like this, delta n with bars, or some people might write like delta n topological n simplex. But I like this for reasons we'll see soon because there's a functor associated. So basically the 0 simplex is a point up to homotopy, and then 1 simplex is just an interval, 2 simplex is a filled in triangle, and then 3 simplex is a filled in tetrahedron, and so on. And for each map in the simplex category, there's a continuous map between associated topological simplices. And this guy defines a functor called geometric realization, which, what does he call it? Yeah, I think he'll call it to be bar. No. So geometric realization goes from delta to Yoneda embedding to presheaves and then the topological spaces. So we'll call this guy the geometric realization functor, and then this the functor that sends n to its topological simplex. Okay, and then evaluation, that's the thing from that earlier thing. So given such a functor from a simplex category into top, we can evaluate it to get a functor from top into set of presheaves, which are simplicial sets, and we'll call that sing. That's a singular simplices functor. Singular simplices functor. So that sends a topological space to a simplicial set that's defined in this way. So called sing x, and it sends any set of sections at n is the set of continuous maps between the n simplex to x. Now this is something that shouldn't be strange to you because this is like this forms like a chain complex using all those the face maps forms a chain complex that is what you take in the homology of that gives you like singular homology, for example. So this is something you've probably seen before in algebraic topology. But it's important. So it's a singular simplices functor forms a simplicial set from a topological space. And then this guy has a left adjoint, which I kind of talked about already, but that's what we call geometric realization. That starts with the simplicial set and then forms out of it a space. Okay. Now you can see kind of that the way that this is defined, it'll send, well, okay, so notation for a simplicial set x, we'll call it's x0, we'll call those the vertices or points of x, and then x1 we'll call the edges, and x2 the faces of x. And the reason we do that is informed by this kind of connection between topological spaces. So under this geometric realization functor, it'll send these guys to points of the space, and it'll send these guys to paths in the space, and it'll send these guys to kind of two-dimensional faces in the space. Okay. All right, 1.3, kind of fun one. Cellular filtration, combinatorial properties of simplicial sets. So he defines this thing called an Eilenberg-Zilber category. And that's a collection that's four things, small category, and then two subcategories, A plus A minus, and then the dimension thing that takes an object and associates it, every object in A to a number. That's called its dimension. In particular for us, we're going to take this to be simplicial sets, and then this guy will just give us the dimension of a simplicial set, whatever that means. And it satisfies these kind of properties, that is, A plus and A minus contain all the isomorphisms, and then this is my cartoon. If it's not helpful to you, again, don't worry about it. It's also, I misinterpreted this thing, so this cartoon is not so totally accurate, but given a non-identity isomorphism in this guy, A plus, the green subcategory, then you, the dimensions are in this way. So the dimension of this guy is less than the dimension of this guy, and given non-identity isomorphism in A minus, then it's reversed. So the dimension of this guy is greater than the dimension of this guy. And then any map in A has a unique factorization of a map in A minus and a map in A plus. And given a map in A minus, there exists a map going backwards. There exists this guy. Such that composing with this gives you the identity. Okay, kind of abstract. The first time I read this, I was really annoyed with how abstract it was, but here's an example. So our simplex category is an Eilenberg-Zilber category with delta plus being the monomorphisms, this being the epimorphisms, and the dimension just giving you just the number n for each thing. And then we talk about degenerate section. So let A be an Eilenberg-Zilber category, given a presheaf and a section X in XA. We say that this section is degenerate if there exists a map lower dimension factors. So a map A to B with the dimension of the dimension of B being smaller, such that this guy has a pre-image, like the pre-image of the section is X. Right. So in particular for simplicial sets, I'm going to write that down. Yeah. In particular, this is kind of abstract, but if we look at simplicial sets, hopefully it'll make more sense. So let's take the category of simplices and take a simplicial set. Then we say an n simplex is degenerate if there exists a simplex of smaller dimension. So an n simplex we can confuse with maps from standard n simplex into X, right? As we learned from Yoneda, and we say that's degenerate if it factors in this way. So if there exists such a thing, where m is smaller than n, where m is smaller than such that this commutes. Right. Any questions or comments? Okay, so a section is degenerate, or an n simplex is degenerate if you can write it as a smaller simplex, basically. For example, like if you want a simple example of like degenerate simplex, if you have a let's say X is a point in X naught, right? You can think of that as kind of just a point in some space. You can think of that if you geometrically realize this presheaf, then this forms a space, right? This is why I think of these categories as spaces in some way. This guy is let's say you have a F in edges, and this is a degenerate simplex that factors through this guy, right? If this is degenerate, then it should factor through as a point. The only degenerate kind of simplices of this form are just identity maps from X to X, right? So given any simplex, you can form a degenerate thing by just sticking in an identity thing. That makes sense. We'll see more of that sort of thing. I think I drew an example later. So, okay. So given a degenerate simplex X in XA, we call a pair BY, where B is, this down. B is in A and Y is in X sub B. So we call such a pair decomposition of X. That is you're remembering the section that it decomposes into and the point in A where that section lives, and that's the decomposition. If it's not degenerate, then you call it a non-degenerate thing. Okay, and then and skeletons for any n, we form a sub presheaf called the skeleton of X, and it's defined in this way. So basically, just contains all non-degenerate things up to that level, up to level n, right? So skn x m, a set of sections, m dimensional sections of this guy are just the same as X for all the way up to n, and then for greater than n, it just consists of degenerate simplices only, right? This guy ends up forming a functor from simplicial sets to simplicial sets. Yeah. Okay, so let's look at some examples, which is what I was trying to draw earlier, but take this presheaf, take this simplicial set, the standard simplicial set, which you can draw in this way. It has 3 points, 3 edges, and then one face like that you can think of as filling in this triangle, right? Now there's a 2 simplex. This is the face. This is this face, right? Filling in the triangle. Oh, sorry. That's not what I meant. So there's a two simplex formed by this functor. Again, we can confuse simplices and maps, right? So we can think of a two simplex as a map from delta 2 into delta 2. This for us is x. And we can form such a map that does this, from 0 to 0, 1 to 1, and 2 to 1. So that forms such a simplex that has 0, 1, and 1, and an identity map here. And obviously this factors through a one simplex. This is just the edge, right? This is just this edge. So this just corresponds to that edge. So it's kind of like taking this edge and just fattening it up by adding a degeneracy with this identity map. Okay, so another way of thinking about this is that this guy factors through this edge, right? The edge 0 to 1. Which is what I said here. Now, let X be a section of such a presheaf, then there's a unique decomposition into a non-degenerate section. So any section can be distilled into some non-degenerate thing of lower dimension, right? So often we'll just kind of reduce ourselves to thinking of non-degenerate sections because any section, any simplex can be written as a non-degenerate one. And then there's a special presheaf called the boundary of given a representable presheaf. So the boundary is written as a skeleton. Okay, so take a representable presheaf HA. Its dimension is the dimension of A. Subtract that by 1, so 1 dimension less. Throw away all the top dimensional simplices, basically, and then that's your boundary. And this kind of agrees with, intuitively, this agrees with the boundary, the topological boundary, like of a topological simplex. So you can verify that. I think he also mentioned that. I should mention it in the book. And then there's this theorem 1.3.8. So basically, for any n given such presheaves, X a sub presheaf of Y, and both those are presheaves over some category A. Let this guy be all the sections that don't live in X, all the sections in Y that don't live in X, and then of dimension n. Then there's a push-out square of this form. So collect all the boundaries of things that are dimension n that don't live in X, and then fill those in. And then push out from the n-1 skeleton of Y into the n skeleton of Y. This is just me trying to write down what this meant. But that's the theorem. And this kind of should remind you of, I don't know if I wrote that down, but this should remind you of how you construct a CW complex. So in algebraic topology, you construct CW complexes by gluing S and I always get confused with the dimension of these guys. This is Sn-1, I think this should be Dn. But maybe backwards. But the way you construct CW complex, right, the CW complex X is by filling in spheres into Xn-1 to Xn. Right, so this is what he means by cellular filtration. And this, I think, by a junction using that geometric realization thing will give you something like this, the CW complex. Okay, and then he talks about, this is kind of technical, class of presheaves being saturated by monomorphisms. I won't go too far into this because it doesn't show up immediately, but check the book, he wrote all this down. It is 1.3.9. Yeah, that'll show up later, and we can just review that when it shows up. I think it shows up in chapter 3, something like that. Given a class of presheaves that's saturated by monomorphisms and contains all representable presheaves, then it is the entire set or the entire category of all presheaves. That's that corollary. This thing is what I was talking about CW complexes. Getting ahead of myself, but this is what I was talking about. So taking this under geometric realization gives you a push out square like this, and -1 skeleton and n skeleton. This. And this should remind you of CW complexes. So given any simplicial set Y, then a geometric realization is a CW complex, which is nice because CW complexes are nice to work with, right? Then, okay, given a Eilenberg-Zilbert category A, such that any representable thing has only finitely many non-degenerate sections. For example, our simplex category is such a thing. Then for any finite simplicial set X, that is an X with finitely many non-degenerate sections, i.e. a finite simplicial set. So for any finite simplicial set, then this functor, the Hom functor from X blank, commutes with filtered colimits. Filtered colimits is a whole thing which we can talk about if you haven't seen that, but basically it just means like any sub diagram, like a small diagram, has a colimit. It's just what makes it filtered in some way. Okay, that's basically section 1.3. Any questions or comments? I really wanted to get to like 1.4, 1.5, but I didn't actually write down notes for those. So I can still talk about them, but it might take a little longer. But any questions on the stuff that we talked about? Good. Okay. Oh, I did write down a little bit about nerves. So we'll talk about it. As I said earlier, when we were talking about the simplex category, we can think of these finite posetsets or elements in the simplex category as categories themselves, right? The objects are 0 up to n, and then there's a single map if I is less than or equal to j. This is my way of writing a singleton. And then if I is greater than the j, then there's no maps, right? So and you might draw like 0 to 1 to n. And then obviously any two things you can compose them into. So all that is to say, we can think of the simplex category as a full subcategory of category of categories, or category of small categories. Then using that evaluation thing this is from 1.1.10 again, gives us a functor called the nerve. So by definition, what that does is it takes a category and it forms a simplicial set called the nerve of that category, and C and n simple C's of these are just Homs from this guy into C. And if you work out what that means, that is they give you strings of n composable morphisms in C. Okay, and then from that theorem 1.1.10, we saw that this guy has a left adjoint, which we call I shriek, whatever. He calls it tau for like, I think in Joyal he uses tau. I don't know who else uses that, but I used H, and Brewer uses H for homotopy functor. So basically, given a simplicial set, it forms a category called the homotopy category. And he doesn't go into detail about this, but we'll talk about how to write this down more explicitly with what he calls the Boardman vote construction. And this will show up constantly. Like this is an important thing. So we won't go into detail about this right now, but we will. If not today, then certainly next time. This you can ignore. This is just filming notes. Okay. Okay, so these are all the notes I wrote down, but I can keep going, or I can just stop there and we can maybe just digest what we do. So I think we should just stop because we only have 5 minutes. Any questions or comments? Or... No?
Well, what do you mean by that it flattens out homotopical info, or were you wanting to talk about that later?
Yeah, yeah. Well, we'll see that more explicitly later, but we can talk about it informally. So, let me just stop the recording.